Okay, now you've had a chance to play around with the cat function and come up with a list of values, and then with those list of values from inputs and outputs, you're able to pick out what is the symbolic or the pattern, right? And what's the rule? What is the rule that the cat is using to come up with these outputs? So I'm going to show you all the shortcuts and all the easy ways to be able to jump straight from inputs into symbolic representation into the graph, and being able to switch back and forth between all these different tools. So first, let's take note of some of the important um, terms that are used in these linear functions. So we have one term. So term is anything that's separated by a plus sign. So one term will have a variable attached to it, and this is our unit rate of change, right? So each step it's going up by 3 more. And then we have this other, the one that's just a number by itself with no variable attached to it. We call that the constant term. So linear terms could be 3x or 2n or 1/2 n or 6a. These are all linear terms. Constant terms are just single numbers. So you could have 1, or in this case 2, or 5.5, or 3/4. If it's a number by itself with no variable attached, it's a constant term. So how do these terms affect the values that will come out, and how do they affect the graph that will be made from this function? So here's all the shortcuts, right? So let's talk about the constant term first. The constant term tells you your initial condition, and maybe you figured this out with a cat function, but every time you put in a 0, what happens to your linear term? 0 times anything is just 0, isn't it? So 0 makes that drop out, and then you're just left with a 2. So we call that our initial condition. When x is 0, what is your function value? Or our function is y. So what is the y value when x is 0? And in this case it's 2. So I know this is where it crosses the y-axis. So we call this initial condition. We call it our y-intercept, or we call it, a lot of times we write the linear functions like this: y equals mx plus b. So we call that b. It's the number by itself. So that's it, basically. You plug in 0 for x and you find out what the value of y is, and that's going to be your y-intercept. And anytime you see anything, y equals 1/2 x minus 7, I can look at that and say right away it's going to cross the y-axis at -7. If I see y equals, I don't know, 3x plus 1/2, right? I see this half, and I know immediately that it crosses the y-axis at 1/2. So that's all it is it's the number by itself, and it tells you where it crosses this y-axis. It's the initial condition when x equals 0, right? X goes 0, 1, 2, 3 out that way, and -1, -2, -3 out that way. So when it's at 0, you're on the y-axis. Okay, that's the initial condition. The other term, so another way to write this, right, was y equals mx plus b, where m is your linear term and b is your constant. Okay, so let's look at the unit rate of change. So remember when we looked at this, we had, so 0 is 2, then one more is increase it by 3, right? 3 times 1 is 3, plus 2 more is 5, and you see that each time it's increasing by 3, so the next one should be 8, right? If I do 2 times 3 is 6, plus 2 more is 8, increased by 3. So each time you go over 1, it's going to increase by 3. So it's starting out at 2, and it's going to go up 1, 2, 3, and then it's going to go up 1, 2, 3, and then it's going to go up 1, 2, 3. So this point right here is 0, 2. This point is 1, 5, and then 2, 8, and then it'll be 3, 11. All right. So each time it's increasing by 3. So how does that number affect the graph? Well, it makes this line, if it's a bigger number, it's going to be steeper, right? It's going to increase more. And if it's a lower number, if it's a half, it's going to only go up a half to there, right? So it would be a line like that if the linear term was a half. So if it was 0, what would happen? It would just go away. 0 times anything is 0, so this would always be equal to 2. So y would always be equal to 2. And it would just be a flat line. And what if it's negative? So that makes it go down from 2, right? So negative 1 plus 2 would be just 1, and it would start going down, right? So these are negative numbers for that linear term. So what do we call that? We call that the slope. And it tells you the steepness, right? The steepness of the line. And it's a unit rate of change. We call it m. The unit rate of change. Some people like to think of it as rise over run. It's a useful way to think about it because sometimes if your slope is a half, right, you don't want to say, well, I'm just going up a half for each unit, right? So if it was y equals 1/2 x plus 1, right, what happens? Well, each time it's going up a half, but some people don't like picking out where it is to find a half, so they like to think of it as rise over run. So it goes up 1 for every 2 that it goes over. So that's another way you can do it. So rise over run, it's a change in y over a change in x. Oops. So I like to use delta y over delta x. That's what this mathematical symbol for change is. Delta changes difference, the difference in the y values over the difference in the x values. So, and the slope is the same throughout the whole line. So if here I'm going up 1 over 2, so say plus 1 here and plus 2 there, well, it's the same if I do another plus 1 plus 2 plus 1 plus 2, right? And it would be the same if I thought of it as going up 2 and over 4, right? So these are equivalent fractions, right? Up 1 over 2 is the same as up 2 over 4 is the same as up 3 over 6. So we have these triangles that are all equivalent in similarity to each other. So that's the way you can also think of slope, is change in y over change in x. So what we're going to do is build a GeoGebra model that we're able to rapidly change all of these slopes, so we can look at what happens, and we can also change our constant term to see what happens when we change that. Okay, so that's up next.